SHM, simple harmonic motion. Oscillations can be forced and free. A free oscillation is where it oscillates at its natural frequency. These oscillations are a maximum at the centre and zero at the extremities because the kinetic energy is maximum at the equilibrium position, but is zero at the extremity of this oscillation. So when the kinetic energy is a maximum, the potential energy of the oscillation system is zero. But when the potential energy is maximum, the kinetic energy is zero. So we have some definitions. So displacement is the distance from the equilibrium position, measured in meters. Amplitude is the maximum displacement, measurement in meters. The time period is the time for one complete oscillation, measured in seconds, and the frequency is the number of complete oscillations per unit time, measured in hertz. So this is a displacement against time graph, and it is a sine curve. And from this we can see in this slide you can see the equation for angular frequency, which is the frequency of oscillations expressed in radians per second, which is equal to 2 pi over t, but t is 1 over f, so angular frequency is equal to 2 pi times frequency. And this can be seen on a graph as x equals amplitude times sine times angular frequency times time, where x is the displacement from the equilibrium position, a is the amplitude, omega is the angular frequency of the oscillation, f is the frequency of oscillation. For these equations your calculator must be in radians, as 2 pi f is measured in radians. You can also work out the maximum velocity from this by 2 pi f times the amplitude, where again amplitude is a is the amplitude, f is frequency, and v max is the maximum velocity. And here we see phase and antiphase, where phase is the fraction of an oscillation between the vibrations of two oscillating particles, expressed in degrees or radians. And the phase difference is the difference between two separate oscillating objects have travelled through a complete oscillation. Two objects that are at the same point through oscillation will both form a displacement time or velocity time graph with the same pattern, and they are considered to be in phase. For example, two objects that are both at the same maximum positive displacement at the same time. If two objects have a phase of 2 pi radians or 360 degrees, they are still in phase. But if two objects that are at opposite points through a oscillation will form a graph of an opposite pattern, they are considered to be antiphase. For example, if one object is at maximum positive displacement when the other is at maximum negative displacement. SHM. Some oscillating objects are said to be performing simple harmonic motion. Where in SHM, if the acceleration of the object is directly proportional to its displacement and is always directed towards the equilibrium position. So the definition of SHM overall is the motion of an oscillator when the acceleration is proportional to the displacement from the equilibrium position and is towards the equilibrium position. The mathematical equation that can help define SHM is minus 2 pi f all squared times displacement, where a is the acceleration, omega or 2 pi f is the angular frequency, f is the frequency, x is the displacement. And so the maximum displacement is either plus or minus, considering whether the maximum displacement is a maximum negative or a maximum positive. So if the maximum displacement is a maximum negative, the equation is a plus. If it's a positive, the acceleration is minus. So here we can see three graphs: the displacement against time graph, the velocity against time graph, and an acceleration against time graph. In the bottommost corner here you can see that there is a table showing the difference between the three individual graphs. So here we have forced oscillations and resonance. When a driving force is applied to an oscillating system, the system undergoes forced oscillations, and the response of the system depends on the frequency of the applied force and the natural frequency of oscillation of the system. The closer the driving frequency is to the natural frequency of the system, the more energy is transferred. If the driving frequency is equal to the natural frequency of the system, maximum energy is transferred and maximum amplitude is reached by the system. This is called resonance, and the frequency it occurs at is called the resonance frequency. Resonance, when the forcing frequency matches the natural frequency, the amplitude is a maximum and the energy transfer is also a maximum. Some examples of resonance. Pushing a child on a swing, your pushing frequency should get close to the natural frequency of swing to transfer maximum energy and provide a maximum amplitude, so overall you have to use less force. Microwaves also use resonance, whereby the frequency of the microwaves match the natural frequency of the water molecules in the food, so they resonate and maximum heat energy is transferred. These are useful examples, but some more so dangerous examples are suspension bridges, whereby wind can blow against the bridge and the frequency of the wind can cause the bridge to resonate and potentially collapse. A real-life example of this would be the Tacoma Bridge collapse in 1940 due to wind. So, damping. Damping is the use of material to take energy out of an oscillating system, thus reducing the amplitude of the oscillations. Without damping, the amplitude and therefore energy of a resonating system would increase continuously, as shown in the graph. But with damping, the amplitude and energy will increase until energy is being removed at the same rate as it is being supplied. And here you can see the three sort of different types of damping. So we have light damping, which shows a highish curve, medium damping, which shows a medium-sized curve, and heavy damping, where it is very low in terms of its amplitude. So use of the damping. Damping can be used in the foundations of buildings to absorb earthquake shock waves. This means that the building will shake much less in an earthquake and overall will suffer much less damage than it normally would. And here we have an example of a question. This shows masses on a spring and how it will be released to oscillate vertically with simple harmonic motion. Two students make different predictions about the relationship between F and M. One student suggests F is proportional to 1 over M, while the other believes F is proportional to 1 over the square root of M. So how would you go about doing this question? You'd start off by obtaining readings for a set of different masses and then record the time period for each mass. You'd calculate the frequency using 1 over F and then plot graphs of F against 1 over M and a graph against 1 over the square root of M. The graph, which is a straight line through the origin, is the correct. To make this more reliable, you could count to more than five oscillations, maybe go 10 and 50 and then divide by that same number. Time oscillations from equilibrium position, you could use a marker to have a much more precise point of where the end of the oscillation is, and take repeat measurements of t and find an average overall. So here you can find the maximum kinetic energy of the masses. So here you want to use the equation we looked at earlier, which was the 2 pi f times the amplitude to find the maximum velocity. So you have the amplitude, you have the period, and to work out the frequency for that you want to do 1 over t to find the frequency. From this you can get Vmax, which is 3 pi over 50. And then you want to put this, because you have the velocity now, you want to put this into the kinetic energy equation, which is half mv squared. So you'd have a half times 400 times 10 to the minus 3, because it's in grams or kilograms, and then times 3 pi over 50 all squared. So overall the final answer is 7.1 times 10 to the minus 3. Then you want the maximum acceleration of the masses. So here you want to do A max equals 2 pi f squared times amplitude. So you'd do 2 pi times 1 over 1.2 again, like we did with the frequency. All that squared times 36 times 10 to the minus 3, because it's in millimeters. And then you have the maximum acceleration of 0.99. Now you want to list the different types of energy in oscillations of this mass spring system. This was shown in the second slide of the presentation, whereby the kinetic energy is 0 at the lowest point, but increased to a maximum at equilibrium position because it has a maximum velocity at equilibrium position. But the potential energy, as the masses move away from the equilibrium position to the extremities, because at the extremities kinetic energy is 0, but the potential energy is maximum. You have strain elastic energy as well, decreases as masses rise from lowest to the highest point